And this was actually what we call as the permutation rule 2. So, you know, we of course talked about factorials, and then we looked at the permutation and combination formulas last time. So this one here, there we go. You know, what happens if you are actually trying to do permutation of identical items? And you know what that means is, you know, if a quantity is repeating. So they're talking about, you know, if you have the 3 letters that make up the word saw, how many different ways can we arrange that? So, you know, you've got 3 letters in there. So that would be choosing 3 letters out of 3 letters, and you would do a permutation calculation on that. And you can see there's 6 different ways that we can arrange these 3 letters SAW, and you can see what those 3 different arrangements might, you know, end up looking like. But what if you had a word, because, you know, in SAW, SAW, they're all 3 different letters, but what if you had a word like C, you know, SEE, and you can see that's where the E's are repeating. So if you follow the same idea as the permutation that we did here with saw, you know, you did 3 out of 3, we would say, well, there's 6 different possibilities that we can come up with. And you can see we are, you know, using blue and red for the 2 different E's, so that you can kind of see what happens when you rearrange them. So you can see over here, the red E is first, and then the blue E. The blue E is first, and then the red E. And you will see again, it's just the colors that we keep switching places. But if you really think about it, you know, both of these first 2 are the same word, same arrangement. These 2 are the same arrangement, and these 2 are the same arrangement. So technically, you know, we only came up with 3 arrangements and not 6 different arrangements like you saw over here. So in these type of examples is actually where we're bringing in this new rule for permutation with identical items. So we actually, you will see, modify this equation a little bit. We are saying, okay, we've got 3 different letters, but technically you only have 2 alphabets, S and E. So you will see when we do 3 factorial divided by 2 factorial, we get with 3 different arrangements instead of 6 different arrangements. So that's actually what brings us to this formula for permutations of identical items. You will see you actually start out with, you know, the total letters you have, but then depending on how many identical letters you have, you actually have to do a permutation on each one of those identical items. So let's take a look at this example here. They're saying the number of distinguishable permutations, you know, how many will be there when you use the letters from the word Mississippi. So if you take a look at this, you know, that's a total of 11 letters in the word Mississippi, but you will see the letter I is, you know, being repeated 4 times. So you can see 1, 2, 3, and 4. The letter S also gets repeated, you know, 4 times, and then you will see the letter P is also getting repeated 2 times over here, and you know that only leaves you with M, and basically M is being repeated just once. So technically you can actually write this down as 11 factorial for all the 11 letters. Then you can have 4 factorial for I being repeated 4 times, 4 factorial for S being repeated 4 times, and then 2 factorial for P being repeated, you know, 2 times. And then technically you can actually also add 1 factorial for that M, you know, the letter. But we know 1 factorial is just going to be number 1. And that's the reason why they did not include it in here, because it doesn't change your calculation. So you can add the 1 for the M from the Mississippi, or you can leave it. But there are 34,650 different ways that we can actually rearrange these letters. And that's taking into consideration that, you know, those letters were repeating multiple times. Now, if you did not use this calculation, you know, the permutation for the identical items, and if you just did 11 out of 11 letters like we showed before, if you actually check your permutation calculation for that, you will actually see you are going to get a much larger number if you just did 11 letters out of 11 letters, not taking into consideration all the different repetitions that we have there. So you can see this is coming out to be 39,916,800 different arrangements. And, of course, that tells us, like you saw with the letter from the word C, some of them are going to be repetitions. So you can see that makes a big difference between using the two rules for our permutation. So remember, this one here is for permutations with identical items. And that's what it would come out to be. And actually, they're also showing you the same idea if you did just 11 factorial. That also ends up giving you a pretty large number, with the arrangements. So let's take a look at an example here from our textbook. Okay, let's do this one over here. So they're asking about find the number of permutations of the letters in each word. So let's do this one here, 56 for Philadelphia. So how many different permutations can you come up with? First you have to see how many of these are being repeated. So for the letter P, what would you say? How many times is it being repeated? Yeah, Philadelphia will have 2 E's, so that will be E and P over here. What about H? Okay, so that's H also twice. Very nice. I, that's 1 and 2, so that's 2 times for I. What about L? Yeah, very nice, because that's 2 L's. Okay, and then A? A is once. No, A is also twice, right? 2 times for the A. And then what does that leave us with? D and E, right? And they're going to be 1 each. Okay, so once you have those repetitions taken care of, then remember, this is where if you add all of these together, what's that? 12 letters? Yeah, very nice. So that's a total of 12 letters. So that becomes our n value. So that would be the n factorial. And then remember how they had the x, y, z factorial on the bottom, which, for us, that number will be a little bit bigger. So you will be doing 12 factorial on the top and then dividing it by 1, 2, 3, 4, 5 for each one of these. And then if you wanted to, you don't have to, you can also add the 1 factorial for the D and the E. So how many permutations will this end up giving us? Okay, Isabel, you've got 239,500,800. Okay. Can somebody verify that number, or did you get a different answer than what Isabel has over here? Okay, so Macy, you've got quite a bit smaller number, 14,968,800. And looks like Lorena, you had the same thing. So Isabel, what happened? Looks like you have quite a bit larger number. And what I can think of is that if you did not have enough of those 2 factorials in the denominator, that could have, yeah, that's what I was about to say. That's probably why you're getting a larger number. And yeah, so make sure you have 5 of these, 2 factorials in there, because if any one of them is missing, your answer will be incorrect. So, okay, very nice. 14,968,800 permutation. So just look at that, how many different ways we can arrange just taking the letters from the word Philadelphia. And you can see there are a bunch of different examples kind of having you do the same calculation over here. Okay, so let's clear this out. Okay, so I actually wanted to look at just a couple more examples from here. So let's look at number 28. And this one is talking about, just as your instructions, they're saying refer to a deck of 52 playing cards. Again, jokers are not allowed. And then they want to know how many 5-card poker hands consisting of all hearts are possible. And then the second one is saying how many 5-card poker hands consisting all cards of the same suit are possible. So again, if you need to see what a deck of cards looks like, you can click on this. Probably went too far. Okay, so basically, it's going to be the suit of cards going from the face cards, your king, queen, and joker, the ace, and then, numbers 10 through 2. So using that as your reference, how many 5-card, like they said, poker hand can you create consisting of all hearts? So what would we need to do for an example like this? And what calculation would you use? Permutation, combination? Then is the order important or not important? And that's kind of what's going to help you decide between the permutation and combination. Okay, Burgundy, you are saying permutation. So you're thinking in the order that we select these cards will be important? Okay, then Ethan, you said permutation for sure. Burgundy, you're saying no. Aaron and Isabel, you guys are going with combination. So Ethan, again, you are also, since you're saying permutation, you're thinking that the order would be important, right? In which order you select the cards? Because that's the only difference between permutation and combination, right? Because for one of them, when we're saying order is important, we're saying, are you picking, a number card first, like a 5 or a 6, and then you pick a face card? So is that order important in which order you pick the cards, or does it matter as long as any of them are a heart, is it okay? As long as it's a heart card, and then the order doesn't matter. So in this case, the order is actually not important, because they just want to know, how many different ways can we choose a 5 card, poker hand, which will be hard. So remember, in this case, there are 13 cards, which will be, the heart suit, and then you are choosing 5 cards out of that. Since the order is not important out of 13, you are choosing 5. So how many different combinations can we come up with? So what do we come up with for this one? Okay, Ethan, 1,287. Can somebody else verify that number for me, please? Alrighty, Molly, very good. Lisbeth, alrighty. Okay, so you can see there are basically 1,287 different ways that we could end up getting a 5 card poker hand where all of them are hearts. The same thing on the second one, but now they're saying for a 5 card poker hand, they want cards from the same suit, which means they are saying they can be hearts, they can be diamonds, they can be spade, or they can be clubs. So how would we come up with that calculation? So all of them could be hearts, could be diamonds, could be spades, could be clubs. So how many different ways can we do that? How would you do that calculation? Macy, Cooper, are you guys still there? Because I can't see you. So what do you think what we need to do for part B over here? How do we come up with, those different possibilities for, you know, all 5 cards being from the same suit? Come on, guys, I need some input from you because, this is about you learning, not just about me talking. Okay, Isabel, you're saying 13 minus 5 factorial 4 times? Or you're thinking 52 factorial? So Maribel, you're saying for this one, would you find the ones that are repeating in the sets? So Isabel, you were kind of on the right track in terms of the 4 times, but we don't actually have to do the 13 minus 5, because we know if you wanted the same suit, which is what we did with the all hearts, that's going to be the calculation of 13 out of 5 as a combination. So we know for one suit it's going to be 1287, and since there are 4 different suits for part B, you are actually taking 4 times this 1287 to come up with how many different possibilities, because we know for one suit it can be 1287, because we could have changed that hearts to clubs or diamonds or spades as easily, and the calculation would still have been the same. So you're just doing 4 times 1287, which will of course come out to be 5148. So just multiply the answer you got from part A into 4, and you will get your answer for part B. Does that make sense? Yeah, very nice, Aaron. So, not all calculations have to be, the big, long um, calculations with our combination permutation. Sometimes, as you saw with this one, it can be a little bit more straightforward. Okay, let's take a look at one more and then we'll move on to the next section. This one is referring to lotteries, and they're saying the order in which lottery numbers are chosen does not matter. And we are looking at number 38 over here. They want to know which lottery would be easier to win, 5 out of 39 or 6 out of 49, and why. And they're actually asking us to use exercises 34 and 36 to help us out. So let's take a look at those. They're saying a 5 out of 39 lottery, and this is number 34, requires choosing 5 numbers from 1 through 39. This type of lottery is played in all of these states, so they wanted to know how many different 5 out of 39 lotteries are there. So we're not really answering that question. We just know 5 out of 39 lotteries is choosing 5 numbers from 1 to 39. So it will definitely be beneficial for us to know how many different tickets there are. And then 36 is saying 6 out of 49 would of course be choosing 6 numbers from the numbers 1 through 49, and how many different options would be there from that. So they want to know, out of these two, which lottery would be easier to win. So looking at the options from 34 and 36, how many tickets will there be for the 5 out of 39 lottery game, or whatever you call it? So basically for this question, the idea is we have to figure out what the answers for 34 and 36 is going to be. And then depending on, how many tickets each of those lottery generates, then we would kind of have to see, which would be easier to win. So let's talk about 34 first. What do you think you will do here to come up with how many lottery tickets we will have from that 5 out of 39 game? And remember, in the instructions, they told us the order in which you choose the lottery numbers is not important. So to do that calculation again, are you using permutation or combination? And what answer will you come up with? Very nice. Yes, it will be combination, because they specifically told us the order of the numbers is not important. So now tell me, how many lottery tickets will we have, for example, 34? Come on, we know it's a combination. So what calculation are you doing? Because I know when you see these examples on your homework, then you will have no idea how to move forward. So I need you guys to participate. Otherwise, you know, we're just wasting time sitting here. No, the n is all the total numbers you're choosing from, right? So since you're going from 1 to 39, your n is actually going to be 39 numbers because you're choosing 5 numbers out of 39. So it's going to be n equals 5 and sorry, n equals 39, r equals 5. So how many different possibilities do you come out with? Cooper, 5 over 39 is what the game is called, but that's not actual calculation. So Burgundy, in your formula, you just need to change your numerator. Instead of 5 factorial, it would be 39, since n is 39. Yeah, yes, Isabel, that looks good. So what does our final answer come out to be when we do? Ooh, Burgundy, that's too large. Isabel, that looks good. 575,757 different lottery tickets. Alrighty, very nice, Molly, Elizabeth, Kiara, Maribel. Yeah, those numbers look good, Ethan. It looks like you're missing a 7 in that, Ethan. But yeah, that's basically the different, how many tickets you will have. So obviously, you know, we'll do the same calculation for number 36. So in this case, they are saying choosing 6 numbers from 1 through 49. So out of a total of 49 numbers, you're choosing 6. And what will that come out to be? So Ethan, that second answer does not look right. Either you're missing some digits in there. Isabel, you had 13,983,816. Okay, very nice. So now tell me, now that we know what each of these amounts are, how many tickets each one of these games generates, which game or which lottery will be easier to win? 5 over 39? And why is that? Okay, Ethan, you're saying 6 over 49. Isabel and Burgundy, you guys are saying 5 over 39. So can you give me a reason why you are choosing the answer you are choosing? Less tickets for 5 over 39. Yeah, Logan, exactly. The less tickets you have, the less people you are competing with, right? So since you have lesser tickets in the 5 over 39 game, those will be easier to win. So yeah. Okay, Ethan, yeah, I was just about to ask you if that helped you out or not. So yeah, easier to win 5 over 39 because of lesser tickets. Or I guess fewer. All righty. I think that I've actually never played any of these lottery games, so I'm actually not sure how the Powerball works. I'm not sure if it's similar to this setup or not. So yeah, it's something I've actually never done ever. So honestly, if you ask me, I will not be able to tell you. All righty. Good job, guys. So that was just a couple examples I wanted us to go over from 2.4. So that's the end of chapter 2. So now we're actually getting into chapter 3, and we're only doing 2 sections from chapter 3, 3.2 and 3.3. 3.1, if you guys just want to go and look over it, they actually just do a little bit of an introduction there. So if you just wanted some reference, you can, but, obviously we're starting with 3.2. And this is actually, we're getting into our probability. So just the basics with probability. And, when we're talking about probability, we're actually talking about uncertainty. So if you look at the examples here, they're kind of talking about, when you wake up, you may check the weather report to just kind of see, is it going to rain, or I would say snow, since we're getting closer to the winter time now. You can check, the traffic report to see, okay, are we going to get stuck in a traffic jam? Do we need to select an alternate route? So there are always these things that we are not certain about, and, maybe there are ways to check for that. So when we're talking about probability theory, we're basically talking about probability being the branch of mathematics where you are analyzing uncertainty. So the first thing we're actually doing is just talking about the terminology and definitions for some of these terms, but you will actually see that there's a big connection between probability theory and set theory, which is what we talked about in chapter 2. So you will see a lot of that terminology, and even the calculations are actually based on what we saw in set theory. And then remember, set theory also had a correlation with logic. So all of these concepts are actually interconnected if you think about it. So just some terms to be aware of when we are looking at probability terms. When we're talking about the experiment, that's of course the process where you are either making an observation or you are getting an outcome from making that observation. When we're talking about a sample space, we're saying it's all the possible outcomes you can get from doing this experiment. An event is basically going to be a subset of your sample space. So you can see how we are using this terminology of, all the possible outcomes. When we're talking about all possible outcomes, you can think of your sample space as being our universal set that we were looking at in chapter 2. When we're talking about subset E, obviously we're talking about anything that will be part of the universal set, becomes your subset. So that's kind of how an event can be described, as a subset of a sample space. So you can really think about, the sample space being your universal set, and an event basically being a subset of that sample space that you have. And then they're talking about, the distinction between the sample space is that the sample space is a concept used in probability theory, but, when we're talking about universal sets, we only talk about that when sets are being used. So again, just to give you an idea of the distinction between these terminologies, just think about the simple act of rolling a die. And imagine this is a regular 6-sided die. So we know each of the faces on the die will have 1, 2, 3, 4, 5, or 6 dots, right? So the experiment itself will be the act where you are rolling the die itself. Your possible outcomes, because your die could fall on any one of those faces, your possible outcomes could be 1, 2, 3, 4, 5, and 6. So all of those possible outcomes put together create your sample space. And again, you will see we are kind of writing these as sets. We are still using those set brackets to write these out. Now, when we're talking about possible events, remember we said events will be the subset of your sample space. So your possible events could be the event that you roll a die. So we could say event 1 is that you will roll a die and get the number 3. If you roll a die and get an even number, then your subset would actually be just the even numbers, so 2, 4, and 6. If we say you roll a die and you get a number between 1 and 6, including 1 and 6, then that actually means is going to be your entire sample space. So this event can actually have all 6 of those numbers, which is of course similar to our sample space over here. So event is basically, what are we hoping to observe? What are we hoping to get as an answer? When you're talking about the outcome, so especially look at that second one where we said roll an even number. So rolling an even number is the event. The outcome would be getting a number 2, getting a number 4, or getting a number 6. So 2, 4, and 6 are called your outcomes, but the event of getting an even number is your event. So there's a little bit of a distinction between, what is an outcome and what is an event. And, we're kind of talking about that here in this paragraph. You can also define events in terms of being a certain event or an impossible event. When we're saying it's a certain event, that means that event is definitely or certainly going to happen. And that actually means your event will be equal to the sample space. So this one over here, number 3, where we said, you roll a number between 1 and 6, including 1 and 6, you will see how event 3 has the same sample space, has the same outcomes as our sample space over here. So that's why event 3 is what we would call as a certain event. An impossible event would be, something that obviously cannot happen. So we will say this is an event which would be equal to an empty set. So, if you talked about rolling a die, a 6-face die, and getting a number 9, we would say that's an impossible event, because if you only have 6 faces on this die, you can get numbers 1 through 6. So there's no way you can end up getting a 9 when you're rolling just a regular die. So that would become an impossible event. So certain event will be that your event is going to equal the sample space. An impossible event will be basically you have an empty set because it will not equal any of those. So they kind of do a little description of that over here that you can kind of look through. So this is just defining the terminology. Now let's actually get into our probabilities, and we will also talk about odds. So when we are talking about probability, we are saying probability of an event, that the event will happen, is a measure of the likelihood that the event will occur. So it's basically a way for us to say, is it possible this event will happen, and what's the probability? So the probability is basically calculating the measurement to see, what are the chances that this event will actually happen. So again, they're talking about, in the terms of how if you roll a single die, the idea is when you roll a die, we don't know which number is going to fall on, right? Because each face has the same chance. You can even think about this in terms of tossing a coin. Just think about it. Tossing a coin, there's an equally likely chance that it could fall on a head or it could fall on a tail. Same thing with rolling a die. You can get a number 3, you can get a 6, you can get a 1. So there's an equally likely chance that it would land on any one of those faces. Same thing with the standard deck of cards. Just think about it. If it's a standard deck of cards, you've got 13 cards for each suit, so that's 52 cards. If you shuffle your deck and pick a card out, there's an equally likely chance that you can get a 3 of hearts, or you can get a ace of spades, or any of those, right? Because if you're just shuffling your deck and picking a card, there's an equally likely chance that we could pick any of those cards in there. So when we're talking about equally likely, we are saying each outcome has the same chance of occurring. So it will be in a rolling of a dice. Since we have 6 different faces, each face has 1 out of 6 has a probability of coming up. So we will say the chance that you will land on a 3 when you roll a die is going to be 1 out of 6. If you're talking about tossing a coin, with tossing a coin, you have heads or tails. So that's 2 total outcomes. And if you land a head, the probability would be 1 out of 2. If you land a tail, the probability will also be 1 out of 2. So you will see they have the same probability. That's what we mean by equally likely. If we talk about a deck of cards, there's a total of 52 cards. So the chance that you will get, like I said, a 3 of hearts, that's 1 card out of 52. The chance of getting an ace of spades, that's again 1 card out of 52. So all 52 cards in a deck of cards, their probability will be 1 out of 52 for each one of them. So this is what we call as equally likely probability for these events over here. So the way we actually do these calculations is you will see they're talking about the rate of success over a total. So how many ever outcomes you have in your sample space is going to go on the denominator. And then how many outcomes do you have in your event will go on the numerator. So again, you can see your formula is going to be the probability of this event is going to be the number of outcomes in the event divided by the number of outcomes in your sample space. So always think about it as success over the total. So that's talking about, your probability calculation, but a lot of times we also talk about, what are the odds that this will happen? And especially, if you are into sports, you will see they talk about odds a lot more than they talk about probability. And a lot of times people actually mistake them to be the same thing. So they'll think odds and probability are the same, but in English, we may use them interchangeably, but statistically, they are not the same thing. So when we're talking about odds, we're saying the odds in favor of an event are the number of ways that that event can occur compared to the number of ways that that event will fail to occur. So actually, when we're talking about odds, we're actually doing success compared to failure. So, if you think about coming back to this example here, if we talk about what are the odds that you will get a 3 when you roll a die? Now, there's only one number, which is going to be a 3 on your, die. So there's only one number that's a 3. So if you roll a die, there's only one chance that you will get a 3, but there are 5 chances that you will not get a 3, right? Because you could get the number 1, 2, 4, 5, and 6. So we would say the odds are 1 to 5 because there's one chance of success, but 5 chances of failure. If you think about the odds with tossing a coin, well, you can either land on a head or you can land on a tail. So if we say, what are the odds that you will land on a head as a odd, we will say the chances are actually 1 to 1, right? Because you will either land on a head or you will land on a fail. So the chance of success is 1 and the chance of failure is 1. With the deck of cards, if we talk about odds, and again, let's say we want to know what are the odds that you will get a 3 of hearts. Well, there's only one card in the entire deck, which is 3 of hearts, which means there's one chance of success, but then that means we have 51 chances of failure, right? Because those 51 cards will not be a 3 of hearts. So your odds would be 1 to 51. So you can see it's a little bit different when we are talking about odds than when we are talking about probabilities. And that's kind of what they are talking about, over here in this example. So the way your odds of an event are calculated is you actually take how many items you have in the event itself, and you're setting it up like a ratio, and you compare it to how many outcomes you did not have in the event. So that you can see is E complement. So the ways you calculate the odds are, again, success compared to failure. So how many ever outcomes you have in the event itself compared to how many outcomes you have in the sample space that are not in the event. So compare success to failure. So let's take a look at these examples here. They're also talking about, in addition to the above meaning, the word odds can also refer to house odds, which has to do with how much you will be paid if you win a bet at a casino. So they're talking about the odds of an event are sometimes called as true odds, uh, and you can distinguish them from house odds. So again, your house odds are basically you will be paid if you win a bet at a casino. So let's take a look at these examples here. Again, comparing between odds and probabilities. So this one, and we've kind of talked about this, is, flipping a coin. They want to know what your sample space will be. So remember, when you are flipping a coin, you can either get a head or a tails. So your sample space can be just two outcomes, H and T. So remember, H and T are the outcomes. What happens when you do the experiment? So your coin will either fall on a head or a tail. So this is what your sample space will end up looking like. They want to know what is the probability of event one, and event one is being defined as getting heads. So you will see here we're defining E1 as getting heads, and then the probability will be, in our sample space, we have a total of two outcomes. In event one, you only have one outcome, so that gives you a probability of 1/2. But when you're writing this as odds, and this is kind of what I was talking about, you take the number in your events and compare it to the number in your complement of an event. So in the event E1, since you have H, in the complement of that event, you will have T. So that's our comparison of 1 to 1. And they're actually just doing this with a couple different more examples here. So now they're saying for part D, if you think of event 2 as being getting heads or tails, so that means your coin can either land on a head or a tail. So you will see event 2 will now actually have both heads and tails. And guys, this is what we would call as a certain event, because you can see this is the same as your sample space, because our sample space also has both H and T in that. So this would be your certain event. And then when you're calculating the probability, since we are talking about you can either land on a head or a tail, so that's two outcomes in our event, two in our sample space. So this is actually a probability of just one. So we know no matter what, you will either land on a head or a tail. So you are always going to find success in this event. And this is another reason why we call it a certain event, because we know it's going to happen no matter what. Just honestly, if you think of one as a percentage, that's 100%. We are saying, yes, no matter what you do, you toss a coin, it will land on a head or a tail. Of course, we're ignoring the possibility of the coin landing on its side. We're basically saying it's going to fall one way or the other. Now, the interesting part is when you talk about, what are the odds of this event happening, getting a head or a tail. So since our event E2 has both H and T as its outcomes, you will see the complement of that event is actually going to be an empty set. So the idea is, if you already have both the outcomes in your event E sub 2, the complement is an empty set, your odds are actually going to be 2 to 0, or you can actually reduce it down and say your odds are 1 to 0, because you will always fall on a head or a tail. So there is obviously nothing that is going to be a failure, because if you fall on a head, that's a success. If you fall on a tail, that's also a success, because that's how we define event E2. So that's why your failure is going to be 0, because you just don't have anything in that set. The last one is talking about, an impossible event and its probability. So since this is a coin that is being tossed, they were saying, okay, if we talk about can we get a 5 when we toss a coin, well, that will be an impossible event, because, obviously by flipping a coin, you're not going to get 5. You will either get a head or a tail. So that's why that probability is going to end up being a 0, and this is what makes it a impossible event, because we're basically saying it's going to be 0% if you think about it in terms of percent, because getting a 5 would be a possibility of when you were rolling a dice, right? But not from tossing a coin. So they're kind of giving you another example, and this time they're using rolling a die. So of course our sample space for rolling a die would be all the different faces our die can land on. So that would be a sample space of 1, 2, 3, 4, 5, and 6. They want to know the event of rolling a 5. So of course, if we're talking about event rolling a 5, that means your subset E1 is going to equal the number 5. Now the probability of getting this event of rolling a 5, well, there's one outcome in E sub 1, so that's going to be 1. There's a total of 6 in our subset, so you can see that's a probability of 1/6. Now, when you talk about the odds, remember this is success compared to failure. So there's 1 success, but 5 failures. Again, like I explained to you before. So just the same types of, explanation that you want to use over here. Again, in event E, they're talking about what is the event and then the probability that you would roll a number below 5. Now think about this. Yeah, Aaron, that's exactly what a sample space is. All the possibilities that you can come up with. And that's going to be based on, what the experiment is and what you think the possible outcomes would be. So before I show you the answer for part E, when we're saying the probability of rolling a number below 5, what outcomes will that event have? So if we call this as event 2, what numbers would we put in here from our sample space for rolling a die and getting a number below 5? What numbers would you put in there? So what numbers would be below 5 from our sample space? So Burgundy, I'm actually asking what numbers would you put in your event as your outcomes? So yeah, I mean, your answer, I can see what you're answering, but I just wanted to know what you would put in the event itself. Very nice, because the numbers below 5 are of course going to be these first 4 numbers. So now when you talk about the probability, this is where we're saying, okay, the number in event 2 is 4 outcomes. And of course you can see that right over here. So there are 4 numbers out of 6, and that's exactly what you had, Burgundy. And then, guys, you're always working with fractions. So anytime you're working with fractions, just reduce them. We always want to reduce our fractions. So your probability actually comes out to be 2 out of 3, 2/3. And then they were talking about what are the odds of rolling a number below 5. So what are the odds? Now, of course, there are 4 numbers in our event 2, which means 5 and 6 would be the 2 numbers which would fall under the complement. So that would be, a success rate of 4, a failure of 2. So 4 out of 2, again, a ratio. You treat it like it's a fraction and you reduce it also. So that's an odds of 2 to 1. So your chances of success to failure is 2 compared to 1. Okay, so let's see if we can do an example from our textbook over here. Let's take a look at, actually I'm going to go back to 3. Okay, so right over here, actually we're going to have to do 1 and 2 before we can use it for the question I want. So this one here is talking about a jar on your desk contains 12 black, 8 red, 10 yellow, and 5 green jelly beans, and you pick a jelly bean without looking. So that's basically the experiment. So you can see when they talk about what is the experiment, the idea is, choosing a jelly bean and looking at its color. Now, can you tell me how would you define this sample space for our jelly bean experiment? So we know the experiment is choosing one jelly bean out of the container and checking, what color it has. But what's the sample space going to look like? Okay, so Burgundy, you're saying 35 or list them out. Remember, the sample space is the list of all the possible outcomes. So if you had to list it out, how would you list it out? Yeah, so that would be the size of the sample space. That's good. So the 35 is if you take all the outcomes from the sample space and add them together, which, of course, would be 12 plus 8 plus 10 plus 5 would end up giving you 35. So we will definitely have a total of 35 out items. And then, just to kind of keep it concise, you can do 12 black, 8 red, 10 yellow, and 5 green jelly beans. And then yes, they would add up to a total of 35. So based on this, what do you think our answer for number 6 is going to end up looking like? So what is the probability that we will select a red or a black? Or you know what, let's wait on that answer. I may want to show you a rule before we do that one. So how about we just do number 3 and 4. So let's start with 3. What is the probability that we would select a black jelly bean? Burgundy, 12 out of 35. Yeah, because they're telling us you have a total of 12 black jelly beans. So the probability that you would select a black jelly bean, remember, so that means you would be defining your event as, the 12 black jelly beans. So that means you would be taking event 1, and that's taking the items you have in event 1, dividing it by the total items you have in your sample space. So 12 out of 35. And of course, we cannot reduce this further because 12 and 35 would have nothing in common. Now, if they ask you for a fraction, then this would be your answer. If they ask you for a percent, and you can see they're saying round it to the nearest 1%, what do you think as a percent? Rounded to 1%, nearest 1%, what do you think this answer will come out to be? And make sure you're giving the correct rounding. Very nice. Yeah, because as a decimal, your answer comes out to be 0.342. And of course, whenever you are working with, very nice, Mark Lee, Aaron, Macy, Burgundy, yeah. So move your decimal 2 places to the right, so that would end up becoming 34.2. But since they're saying nearest 1%, technically you're actually only looking at 34% as your answer. So as a fraction in the reduced form or as a percent. Okay, very nice. Good job, guys. Now, tell me about number 4. What do you think that probability will be? 1 out of 7. Okay, so how many greens did we have? We had 5 greens in, yeah, Markley went with 18. So you can see we are talking about event 2 as being how many green, and we've got 5 greens. So when you look at the probability for event 2, that is going to be the number of items or outcomes you have in event 2 divided by your outcomes in sample space. So there's only 5 in event 2, 35 in our sample space. And yeah, very nice. So you guys are reducing your fraction. 5 goes into itself once. 5 goes into 35 7 times. So reduced fraction is 1 over 7. So yeah, you guys have that. And then looks like you're giving me 14% as your percent answer. So 1 divided by 7 will give us 0.142. And then as a percent, that will end up becoming 14%. Very nice. Good job, guys. Perfect. I kind of wish I had left a little bit more space here, but that's okay. Okay, did anybody have questions on this? Alrighty, so let's clear this out. All right, so I will come back to the other types of examples. I just wanted to get through some more of our notes over here. So this one you can see we're getting into the relative frequency, comparing that with probability. So they are talking about, when we found that the probability of getting ahead when you are tossing a coin is 1/2, they are saying we never actually tossed a coin. We are just doing this more in a theoretical way, just by looking at, okay, we know tossing a coin, you can either land on a head or a tail. And so if you land on a head, that's 1 out of 2 as our probability, using the formula that we have over here. So they're saying it does not always make sense to calculate probabilities theoretically. Sometimes they are saying it has to be found empirically, which basically means, you have to find by actually doing the experiments and seeing what kind of probability you will end up getting. They're saying the way a batting average is calculated. So they're saying, if in 8,389 times at bat, Babe Ruth had, 2,875 hits, we would basically say his batting average was, 2,875 divided by the 8,389, which is actually giving a probability of, 0.0343, or if you convert that to a percent, 34.3 percent. So you can see, obviously Babe Ruth is one of the greatest baseball players we've had, but when you put it in, a batting average example, it looks like, okay, 34.3, not a very high number, but obviously that is a record that he had kept, and I'm not sure if that record has been broken or not. But obviously this is how we would calculate a batting average. So this is what we talk about empirically, because this is where, we know how many times he was actually at bat, how many times he got his hits. Comparing those numbers, we were able to come up with the probability. So basically, depending on what you are looking at, you can find your probabilities either theoretically or empirically. All the examples we did up to until this point was theoretical, flipping a coin, rolling a dice, or, choosing a card from a deck of cards. All of these are what we would say as theoretical probabilities. They are saying if you try to do this experiment of flipping a coin, different times, you may not always end up with that same probability. So they are saying we could flip a coin 8 times, have heads only come up once, and the other 7 times would be a tail. In that case, if you think about your frequency, you're only looking at 1 out of 8 where you are coming up with a head in that. So this is the idea behind relative frequency. So we are talking about relative frequency of heads as frequency made relative to, you know, your total. So we flipped our coin a total of 8 times, and out of those 8 times, only once we got our head. So, you know, your theoretical probability for getting a head is 1/2, but when we talk about the relative frequency with this experiment, you know, we would say it's 1/8. So you can see how it can be very different when you're actually doing these experiments in a way. So just your relative frequency, we are saying if you repeat an experiment number of times and count how frequently a particular outcome occurs, that is what your relative frequency is going to be, the number of repetitions on the bottom and the number of times the outcome that we were looking for actually occurred. So, you know, just simple experiment. If you guys have a coin easily available, you can try doing a little small experiment, you know, flip your coin 4 or 5 times and see how many times do you get ahead when you flip, you know, just a quarter or something like that. And you will see, you know, our probabilities are not always going to end up matching like you saw with this relative frequency over here. The idea is, however, if you do this experiment a small number of times, yes, your relative frequency may or may not be equal to, you know, your theoretical probability. But the idea is, if you do the experiment a large number of times, so if you were to do it instead of 8 times like they had here, if you did it, let's say 1,000 times, which, you know, obviously would take a long time if you try to flip a coin 1,000 times and record your result. But the idea is, if you do it for a large number of times, then your relative frequency will actually get closer and closer to your theoretical probability. And this is actually what we call as the law of large numbers. So here they're talking about, you know, what if you flipped your coin for 100 times, and out of those 100 times you got 47 heads. So your relative frequency would become 0.47. Theoretically, we know our probability is 1/2 or 0.5. So you can see these two numbers are rather close to each other. But when we had 1/8 and 1/2, you know, those numbers are not really close to each other. So law of large numbers basically says that if you repeat an experiment large number of times, your relative frequency will tend to be closer to the probability of that outcome. And this is actually something you will see in your homework. They are going to kind of talk to you about these law of large numbers. And then, you know, they're just getting into a little bit of a simulation over here with the coin toss, and just kind of showing you how initially when your number of tosses were really small, you can see how that you know, relative frequency was changing. But as your number of tosses got larger, you will see this curve is getting closer and closer to this probability of 0.15. So you can see how initially those numbers were kind of going up and down, but then, you know, they started getting a lot more closer to that line for 0.5. And that's what happens with these law of large numbers. And, you know, they're kind of talking about some interesting examples over here with the coin toss. They're saying if we use a real coin rather than a computer, what would happen? So 3 different mathematicians have tried to do this. They're talking about in 18th century Count Buffon. He tossed the coin 4,040 times, and out of those, he got heads for 2,048. So you can see when you do those larger number of tosses, it is getting you closer to that 0.5 or half probability. During World War II, they're talking about South African mathematician John Carriage. He tossed the coin 10,000 times. And, you know, this was during when he was imprisoned. And they are, again, you know, 5,067 were the number of heads. So again, a probability pretty close to 5, you know, half or 0.5. In the 20th century, they're talking about Carl Pearson, again, tossing the coin, wow, 24,000 times. And he got 12,012, which is, again, close enough to that 50%. So if you only do this, 10 or 20 times, that relative frequency will not match. But as these experiments are showing, definitely you can get a nice close relative frequency to your probability. I don't know if you guys are actually familiar with, this is not doing it by hand, but there's this website called random.org. And it actually does have a coin flipper over here, and you can actually choose what coin you want to toss. So you can select the type of coin you want. You can see it actually does all different countries, so you can do that, and then actually tells you how many times you want to toss your coin. And looks like the maximum number here is 200. Oops. Might have gone too far. And for now we'll just pick the first coin that they have listed here. So the idea is, they are going to simulate your toss, and you can see they're showing you for those 200 tosses what you have, so you can kind of do that also. So if you don't want to actually do, so it's just a tiny little experiment that you can do on your own. Alrighty, so remember how we were talking about the house odds and that kind of thing. So let's take a look at this one over here. So again, the idea is the house always wins. That is something you will always hear about, gambling and gambling at casinos or any other kind of legal gambling that's out there. So they're talking about how, probabilities are much more useful, to the casino than they would be to an individual person, because, obviously the casinos are in the business of making money. They don't want to lose a whole lot of money. So they're talking about, just, you can kind of read through this, how the house performs the experiment for a much larger number of trials. The house plays the game so many times that relative frequencies, of course, will end up being exactly the same as, what the probabilities should be, theoretically. And then the idea is, if the house is not gambling at all, it knows what's going to happen. So similarly, they're saying a gambler with a system has to play the game for a long time for that system to be of use. So if a gambler is going to win, they obviously have to play many more times, but that also means you can end up losing a lot more money. So just as an experiment here now, we are talking about flipping a pair of coins, so two of them. So if you talk about the sample space, when you are tossing two coins, you have to think about it this way. Both the coins could land on a head, both the coins could land on a tail. The first one could land on a head, the second one on a tail, or the first one on a tail and a second one on the head. So keep in mind, these two events, these two outcomes are not the same, because this is the distinction of which coin falls on its head and which coin falls on its tail. So even though one of each is showing up, it's really specific to which coin. So these are considered as two different outcomes. So as you can see, our sample space will end up having 4 different outcomes. Now they want to know what would the event of getting exactly one head look like, and getting exactly one head will be these two outcomes, because the remaining 2 outcomes is you have 2 heads or 2 tails. So getting exactly one head is going to be HT or TH. So when we talk about the probability for this event, there are 2 outcomes in this event of getting exactly one head. So that's 2. In our sample space, we have a total of 4 outcomes. So 2 over 4 will reduce down again to 1/2, or you have a 50% chance that we will end up getting exactly one head when we flip these pairs of coins. Now they want to know, using the law of large numbers, how can we interpret this event. So you will see here we're talking about if an experiment again is repeated a large number of times, we know our relative frequency will tend to be closer to the actual probability. So what that means is if we toss a pair of coins as many times, we should be getting closer or hopefully getting exactly to that probability of 50%. But again, keep in mind, guys, we are kind of talking about this more in terms of, you know, performing these experiments and what will happen. But when you actually do this, your result could look a little bit different than what we hope it will. But that's the idea behind the law of large numbers. As many times as you are able to do these experiments, you know, the closer you should be getting to that probability value over here. So let's come back to these questions over here. So this is the same one we just looked at. Let's use this guy again, and let me get my sample space because I erased it. So this was, there we go. So we know we had 35 outcomes in this, and then our sample space itself had 12 black, 8 red, 10 yellow, and 5 green. So let's use that here on number 6. Now this time they're talking about our event having red or black. So what outcomes would you put inside this event 1 for the red or black? Okay, so Markley, can you tell me how you came up with that 20? Very nice. Yeah, exactly. It's really that straightforward. We know we've got 12 black jelly beans and we've got 8 red jelly beans. So when you add them together, you know, our total for the event 1 comes out to be 20 jelly beans. So when we're talking about the probability for this event 1, that means you take the number of outcomes you have in event 1 divided by the number of outcomes in your sample space. So that's 20 divided by 35. As a reduced fraction, what does that look like, guys? 20 over 35 when you reduce it. Very nice, Burgundy, because 5 will actually go into both the numbers. So 5 goes into 24 times, 5 goes into 35 7 times, and then you guys have been giving me the percentage also. So very nice. This comes out to be 0.571. So to the nearest percent, you guys had 57%, and that's correct. Alrighty, so reduced fraction or as a percent. Okay, so let me ask you, I'm gonna keep our sample space, and let's do number 8 next. They want to know what is the probability that it is not red. How will you find that probability that it is not red? The jelly bean that you select from the jar. So our event is going to be not red. So what outcomes would you put in here when they're saying it's not red? Basically, every other color is okay, right? As long as that color is not red, we don't care. It can be black, exactly. It can be yellow, it can be green. So very nice, Burgundy, Lorena. So that can have 12 blacks, 8 reds, and 10 yellows. Just Oh, sorry, no reds. Wrong one. Blacks, yellows, and greens. And that was a total of, I think you guys sent me that, 27. Because, of course, that's 12 plus 10 plus 5. So when you're finding the probability for this event, that's, of course, going to be like you have 27 divided by 35. Again, can I reduce this fraction or not? 27 and 35. Is there anything in common? Because 27 will be 3 times 3 times 3, and 3 will not go into 35. So yeah, you should not be able to reduce it. And then as a percentage, you guys had, let me see. I think I had seen 77%, I believe. Yeah. Because your answer comes out to be 0.771. So again, to the nearest percent, that would be 77%. So again, once you figure out the structure and how these formulas work with probabilities, finding these answers are not that difficult. Alrighty, let's take a look at another example over here. Oops. Okay, so now instead of probability, let's talk in terms of odds. So what are the odds of picking a red or a black jelly bean? And again, our sample space was 12 black, 8 red, 10 yellow, and 5 green. So what are the odds that we select a red or a black jelly bean? Okay, so you've got, let me see. Isabel, you've got 18 over 32. Yeah, I was about to ask you where you're getting those numbers from. And then Burgundy, you've got 20 to 15 or 4 to 3. So you're just reducing that. Okay, so tell me again how we are coming up with 20 and 15 as our original numbers. Very nice. Yeah, because remember, guys, when we were talking about odds, we said that's a comparison between success and failure. So when we're talking about, what are the odds of picking red or black jelly beans, then of course that means you are adding the red and the black together. So that's going to be 12 plus 8 for our success. And that means for our failure, we do not want yellow or green. So you add those together. And, of course, that will add up to your 15. So that's where you are getting 20 compared to 15. And again, treat these like fractions. So both 20 and 15 have a 5 in common. 5 goes into 20 4 times, goes into 15 3 times. So this is actually what your answer will be. So Isabel, did you get that? Yeah? Okay, wonderful. Did anybody have a question on this? Okay, so you'll definitely see you will have similar questions like these with the probabilities and the odds with your homework exercises. Okay, let's take a look at the instructions over here. We're looking at 26. So this one is saying, find the probabilities, find the odds of drawing the given cards, and then they also want us to talk about how the law of large numbers can interpret both these probability and odds. So we're looking at number 26 over here, and this is talking about a card above an 8, and they're saying count the ace as a high. So first of all, let's go ahead and define what this event will end up looking like. So our event, we can describe it as, a card above 8. So what do you think that sample space will end up looking like? Or sorry, the event will end up looking like? Yeah, because a card above an 8 would be your 9, 10, the Jack, Queen, King, and since they're saying use the ace as a high, that would of course also be going as a high card. Oops, that should be a queen. And remember, this is going to be for all 4 of your suits, right? So this will be for basically, do it times 4, because it's got to be for the hearts, diamonds, spades, clubs, all of them, since we're talking about all cards. So can you tell me what the number will be in this event? Okay, check that math again, Burgundy. Yeah, because you've got 6 here, right? 9, 10, Jack, Queen, King, and Ace. So those are 6 cards multiplied by 4. So that's 6 times 4. So you will actually have 24 outcomes in this event. Very nice, guys. All right. So the first part was asking us to find the probability for this event. So tell me what that fraction will end up looking like. Because what will be the number for our sample space here? Very good. Yeah, exactly. Because the number of our sample space is going to be all the 52 cards that you have in a deck of cards. So can you tell me what your reduced fraction will end up looking like? 6/13. Is yeah, you are basically dividing both numbers by 4 as your common factor. All righty, very nice. Now, can you tell me what the odds will be? Oops. So part B was asking us to find the odds. Sorry. That should be the number you have in the event itself, and then the number you have in the complement of the event. So since you have 24 cards in the event itself, remember for how many you don't have in there, you'll basically just do 52 minus 24, which is where you should be getting 28 from. And then yeah, Burgundy, I was just about to ask what would our reduced odds end up looking like. So again, you look at 24 and 28, and 4 will be common between both of them. So this will end up becoming 6 to 7 as our odds. And I actually don't know if they want a percent answer or not for your probability. So if they ask a percent answer, you can convert it. And if they don't, then leave it as a fraction. And then, of course, they talked about the law of large numbers over here. So what do you think will happen if we try to apply the law of large numbers over here? Do you think our relative frequency would be closer to the probability we came up with, 6/13? Okay, so Burgundy, you're not entirely sure since you have that question mark on that. Yeah, I mean, again, the idea is when we're talking about law of large numbers, we do expect this to happen. But, again, when you actually perform the experiment, you might see that you may actually need a lot more tries to try and match this probability of 6 out of 13. But, obviously, that's kind of what we talk about in the law of large numbers. That's possible. So, of course, you would have to keep, trying to select a card when you shuffle a deck and you pick a card, and then you would have to see how many times you get a card that is a card above the number 8, and then you would kind of have to see, okay, how many times did you end up doing that? But yeah, definitely that is a possibility that will happen. All righty, very good. So not sure if we will have time to do the next example I wanted to talk about. We can pick that up next time. But basically, the next part we are actually getting into, and it's kind of interesting because we will be talking about, you can see we're doing a little bit of a probability in terms of, genetics. So when you have your dominant gene, recessive gene, and, actually we'll be getting a little bit into that aspect of how we can actually see these probabilities work out with, the genetic traits that can be passed from, the parent to the offspring. And this is not necessarily just in terms of, from people to people, but you can also see this in terms of inherited diseases. But when they're talking about Mendel over here, he actually noticed this when he was studying plants first. So these kind of genetic experiments and these transference of genes that we talk about actually can happen in plants and trees, as well as humans. So we'll pick up from here next time. But it's kind of fascinating, how humans have distinct genetic makeup. So one person's genetic makeup is going to be so different from another one. You actually see that in plants and trees also, obviously animals too, but yeah, even in plants and trees. So we'll do a little bit of that. So our goal for next class is to finish chapter 3 and basically get you guys ready to take your exam. So please make sure you're working on your homework. If you get stuck on anything, you need extra help, reach out to me. Let me know if you need help with that. Okay. All right, guys, have a wonderful weekend. Stay safe, and I will see you on Tuesday morning. Take care, everyone. Be careful. Bye, guys. Ethan, yeah, you can stay back and I will answer your question.
I have a question too, if I can stay back as well.
Yeah, sure. Yeah, anybody who wants to ask me a question. Isabel, you had a question as well. Molly and Elizabeth, did you ladies have a question? Okay, Ethan, go ahead. Would you like me to be alone with you, or you can ask in front of your classmates?
No, I can ask in front of people. I was wondering if there was a way for me to screen share my screen with you.
Yeah, you should be able to. Give me a second here.
My homework basically is just not saving. It's not, it's supposed to save per question or save per, and it says that I only have 6.8% done of the very first homework assignment.
Oh, that is weird. Yeah.
So I was just trying to, and then like some boxes where it says to list out the possible combinations, I can't even like enter a number. So I was just trying to show you what was.
Yeah, go ahead. Let me take a look.
Is it sharing with you right now?
No, I'm not seeing anything. And then Isabel, looks like you also have a question on 2.2. Okay. Isabel, was this the same question you had sent me the message about, or is this a different one? Different one? Okay.
I'm so sorry. I wish I was more prepared.
No, that's okay. Because I'm not sure why it's not letting you share the screen. I made you a co-host, so you should be able to share your screen now.
Do you know what tab it would be underneath? Maybe like meeting?
If you move your mouse, it should show up on the bottom with the share screen in green. And then it should be just the screen option. Okay, Isabel, while Ethan is figuring that out, do you want to walk me through what you have done so far with number 9? Because I'm looking at your number 9. And it's the one with the monetary donations at the college, right? Okay, so what have you tried to do with that one? Okay, so I'm not able to read your numbers, but I see you have your Venn diagram. Okay.
So basically, I was trying to figure out like the U or the universal number, and I was trying to find the like only the people who only donated to the political campaign, and I was like subtracting the inner like the ones that share from it, and it like was a negative number, and I don't know what that.
Okay, yeah, so you should definitely not have a negative number. You know, the smallest number you would have would be a 0. So is it okay if I share the screen? You cannot see your score. We can just see the example you are talking about.
Mm-hmm.
Okay. So yeah, this is the example we are looking at here, and we've got
Because since I got a negative number, I just put a 0 in it to like as a placeholder, and that wasn't right.
yeah. So what are your 3 circles representing?
The political campaign, the medical research, and the environment.
Okay. So they're telling us 95 graduates donated to the to the political campaign. You've got 78 for the medical research and 137 for the environment. They're saying 26 donated to all 3. So, 26 goes in here, right?
Mm-hmm.
Then you had 20 donated to none of the 3. So that would actually be going in your universal box, right? But 20 would be the number outside because they donated to none. 36 donated to political and medical research. So political and medical research would be right here in this overlap with the 36. 44 donated to medical and to preserve the environment. So that would be in this overlap here. And 52 to political and environment. So you have these numbers in the right spot?
Yeah.
Okay. So tell me, what did you do for coming up with this number here for the political only?
I took 95 and I subtracted 36, 26, and 52. But I think I'm just now realizing what I did wrong.
Oh, you okay?
I think I don't subtract the 26 also. Just the 36 and 52.
Okay, so I think this is why you are actually getting the negative answer here, because in these numbers over here with the 36, 52, and 44, we will also need to subtract the 26 from those.
Mm-hmm.
So yeah, you will need to do these calculations here. So let's see what these guys should come out to be. Oops. So for your 36, you would be subtracting 26 from that, so you should technically only have 10 in here. From the 44, you are subtracting 26, so you should only have 18 between medical and environment. And then from the 52, you should obviously only have 26 left behind with the political and medical. Now see if your calculations give you a better answer.
Okay, thank you.
Yeah, you're welcome. So you think you can take it forward from here?
Yeah.
Alrighty. Okay, Ethan, have you figured out what's going on? No? Aaron, you want to tell me what you wanted to talk about?
Yeah, it was on, I thought it was just about one question, but it was actually about two. It was on 2.1. It was questions 14 and 15. I had the hardest time with question 15 because they weren't numbers, they were letters. So that kind of made it harder for me to figure out part C.
Okay, did you get my message yesterday about this?